the Egyptian culture and want to learn more about it, feel free to join us. Today we have a very important guest. We have Dr. Isam Hiki, and for the introduction, please welcome our advisor, Dr. Ahmed Kamal.
Good evening. Thank you for coming here tonight to listen to this interesting and exciting talk about water exploration in the solar system. I'm honored actually to introduce our distinguished speaker tonight, Dr. Isam Hiki, who has made many contributions and has many accomplishments. So if I go over all of his accomplishments, I'll take all the lecture time. So I guess you're interested in listening to him rather than listening to me. So that's why I'm going to be very brief. So Dr. Isam Hiki is a planetary scientist at the Viterbi School of Engineering in the University of Southern California, and also a Rosetta co-investigator at the NASA Jet Propulsion Laboratory. He obtained his PhD in astronomy and astrophysics with a major in space and planetary sciences in 2002 from the Sorbonne University of Pierre and Marie Curie, Paris University. His research interests in space and planetary geophysics aim to understand water and ice distributions in Earth-arid regions, Mars, the Moon, icy satellites, and near-Earth objects. Dr. Hiki is currently a member of the science team of the Mars Instrument aboard the Mars Express Orbiter, the Mini-SAR experiment aboard Chandrayaan-1, the Mini-RF experiment on board of the Lunar Reconnaissance Orbiter, and the Concept Radar experiment on board the Rosetta mission. Before joining the USC, Dr. Hiki was a research scientist in the Radar Science Group at the NASA JPL, and visiting associate in geology at Caltech, tenured associate professor of geophysics at the Institute of the Earth Physics in Paris, France, and the visiting scientist at the NASA Johnson Space Center in Houston. Please join me in welcoming Dr. Isam Hiki.
Many thanks, Dr. Thank you. Good evening, everyone. When I was invited to come to give a speech here, I thought that I would be in a room with 20 people. I'm actually super surprised to see the large number of people in this room that are interested to talk and to learn about the water in the solar system. So I would like to thank you all for the invitation here. And tonight we're going to talk about something that is fundamental for our understanding of our own existence in the solar system and for the evolution of the solar system. And that's something is the distribution of water across the solar system. So first of all, water, we might think that water is only existing on our planet, the Earth, but that's not true. You can find the water in every body of the solar system in the form of vapor or ice or even liquid. So, and also you can find it on the comets and asteroids, as well as all the other bodies of the solar system. So many people ask why we spend money and the time and effort to understand water on Mars, why we go and study the ice on the comets, the asteroids. It's very simple. We cannot understand the evolution of our own planet, the Earth, without understanding as a member of the family of the bodies of the solar system. So if you want to understand how we are evolving, how the climate of our planet is changing, you cannot understand it as a single body or as a unique case. And so for instance, we see climatic changes and climatic variability in every single body of the solar system. And yet we have a hard time convincing many of the leadership that climate change exists. In fact, climate change is a natural and is an anthropogenic evolution of the Earth, but also of other bodies of the solar system have evolved. So for instance, it's known that we observe the melting of the ice sheet in the poles, in the North Pole. And in this image here, you see that we lost about 25% of the mass of water of the Greenland from 2005 to 2008, as was measured by the gravity variation data. And we see that there is a declining mass variability of the Greenland from 2002 to 2013 and beyond, and that variation is continuing. So we are losing more ice on the poles of the Earth, in very simple words. But very few of us know that climate change is not only happening in the poles of the Earth. Climate change also is happening on deserts environment. And actually, if you see the surface of these desert environments, they are as large as the poles of our planet. But what is the implication of climatic variability over deserts environment? For instance, the southwest of the US is a semi-arid environment, so it's a desert-like environment. It's about 25% of the surface of our nation is the deserts. So we are interested to understand these changes. So let me show you if climate change happened only in the poles here, or if it does happen here. So the image you see here is 60 miles by 40 miles, and it's an image in the north of Sudan in North Africa. And that image, you only see the sand. It's yellow. You don't see any evidence of water. If I look to this image, I don't see anything that shows that there was water here one day. But if you use the radar technique, which we work on, to map the subsurface, which basically the first few meters of the surface, what's happened below the sand. And this is what we see. You see? The surface, a couple of meters deep. And in this picture, you see these paleochannel network, these long rivers that are about a few miles in width, and they are tens of miles of long. And these indicate, today they are very dry, but they indicate that a couple of thousand years ago, this desert was wet. And in fact, the deserts have changed. It was wet 20 million years ago, and then it went from dry to wet on a cycle of roughly 20,000 years to 10,000 years. So if you go on the surface in these areas, and if you go make a ground validation, you will not see these rivers. These rivers are in the subsurface, they are dry. So let's assume you are a rover on Mars, and then you land in the Sahara, and you look for the evidence of these historic flow of water, then you will not find them because they are beneath the surface. So the secret to understand the paleoclimatic changes, which mean the history of climatic changes on any planet, is to go in and see beneath the first couple of meters of the surface. And that's the technique we work on, and that's what the technique we develop on the different mission we work on. So, for instance, on Mars, Mars is a Sahara. So these are the image that was brought by Spirit and Opportunity and by the hiking spacecraft. And what I like about this image, that you see the colors here, and you can see how much Mars is red, and you can see how Mars is rich in oxides, and how Mars also is rich in tornadoes, just like here. So there are tornadoes on Mars, and they move the dust. So Mars is a dusty planet. If you want to understand its history, you need to go beneath that dust layer and see what's happening. So again, why specifically Mars is important for us. Mars is important not because we are going to live on Mars, not because we are going to bring water from Mars to the Earth. Mars is important for us because it is the sister planet of the Earth. Mars and the Earth, in very simple words, they are two twins. One of them, our blue planet, is still alive, while the other one is dead. But if we understand how Mars have lost its water and atmosphere due to the climatic changes, I'm not saying that climatic changes were made by any life. There could be natural evolution, and they are. Then we can understand how our climate evolved on our planet, and what is the anthropogenic signature, so what humans are changing to that climatic evolution. And so if you look to these two planets, our planet is the double the size of Mars, and it has a moon, while Mars has two moons. And Mars, if we project the map of the United States, it will occupy about the eighth of the surface of Mars. So Mars, just like our own planet, has two ice poles, one in the north, one in the south. And just like the deserts on the Earth, Mars is covered in an entire way with these dust layer. And in between these the dust layer, we see fluvial-like drainage features. So these are fluvial activity, a transient fluvial activity, which means they happen on a short amount of time at the surface of Mars, and they show that Mars must have lived recently through fluvial episodes. And so the big question is, was Mars a blue planet? And then if Mars was a blue planet, where would be the best place to find the water today on Mars? And again, we're trying to, the aim of finding the water on Mars is to understand how similar Mars is to our planet, and if they share a history, and if they share future evolution. So to do that, there are 3 missions who are dedicated to look to the water and the subsurface of Mars. And these are the 3 instruments I work on. So there is the Mars Express, the SHARAD, the Mars Reconnaissance Orbiter, and WISDOM. And these have 3 sounding radars. They look to different depths in the subsurface. And basically the concept of how this radar works to probe water is very simple. You send an electromagnetic wave from orbit, and a part of that electromagnetic wave hit the surface and produce an echo, and the second part of that wave penetrate and hit the water saturated material and produce a second subsurface echo. That's the simplistic concept of how this sounding radar work. And in fact, everyone here in this room who has a phone can see that concept. Your phone is working not because the wave will go through the doors, but because these waves will go across the walls. It's the same thing. Electromagnetic waves are able to go through the layers of geologic material on the subsurface of Mars and reflect whenever there is water. So these are some of the echoes. In the area of Amazonis, it's an equatorial area on Mars. And with the SHARAD instrument, we see the surfaces here, and then you see the subsurface reflector about 100 meters deep in these areas. And when we combine the different orbits, we see many areas that look like paleolakes or areas of potential past concentrations of water that could exist on Mars. So when we started this project, it was in 1998, and in 2008, 10 years after, we were able to make a full mapping of the polar layer deposits on Mars, which is the pole of Mars, and that was featured on the first on the page of Science magazine. Why it was featured on the first page of Science magazine? In a very simple word, if you look to the polar layer deposits on Mars, which is here, this, you see that this is the cross section of the pole, and using the Sherrod instrument. So you see the basal unit is here, so that's the base of the pole of the ice cap, and you see in this image that it is layered, the sequence of layer. What does that mean? It means that the poles of Mars was not created overnight. It was created by successions of deposits of ice, which that means that water have stayed long enough on Mars to create that pole. And if water have created so much, if water have stayed long enough on Mars, what does that mean? It means the potential for life on Mars. So this is why after that many rovers started to look to the presence of organic material on the surface of Mars. So there was the Spirit and Opportunity, and then there was the Curiosity rover, and this is just to show you the size of these rovers. So what's the second place that is of interest to look to liquid water on Mars, on the solar system, other than Mars? That would be the icy moons. So these are the moons around Jupiter. So like Europa and Ganymede. So Europa is one of the moon, one of the large moon of Jupiter, and the ice, and Europa is covered with an ice crust of 9 kilometers in average, and underneath that ice crust there is a global ocean potentially of liquid saline water, and because of that water is moving, you see the ice is fracturing at the surface here. So the fracture we observe using the Galileo images at the surface of Europa indicate some type of tectonic ice feature which suggests the presence of liquid lenses of ice few kilometers deep beneath the fractured ice. And these are the ones we try to detect with the sounding radar. So that would produce an echo like this echo you see here with the radar. So that's basically show that these oceans are detectable using the sounding radar technique. Another exciting place is comets. So comets and asteroids are two very important bodies of the solar system. Unlike Mars and unlike the icy moons, the comets and asteroids, they move across the solar system. They move from their orbits to potentially have an impact or a rendezvous with other bodies of the solar system. So they are the transporter of ice in the solar system. So the comet basically is a large body made of ice and dust. They form in the far region of our solar system, and then by the gravitational perturbation, they enter the inner part of the solar system and they orbit the sun in a hyperbolic orbit or in an elliptical orbit. So the Rosetta mission is the mission that was dedicated to study a very special comet, which is 67P. So Rosetta mission is I would think is a lesson of science, technology, but also of a human perseverance. And I will tell you why there's a lot of an important lesson we get from this mission. If you look to Comet 67P at night, it's just one point in the sky that move. And the Rosetta spacecraft is it's a larger spacecraft, so you can see it here. And when it is deployed, it is about the size of a half a football field when it deployed a solar panel. So the Rosetta spacecraft is by all means a very special mission. Why? First of all, it has a large number of instruments on board. So for instance, the average, the number of instruments we have on a mission to an asteroid is anything from 4 to 6 instruments. The Rosetta spacecraft have 21 instruments. 21 instruments, and 21 and 4 of these have never been flown on any space mission before, like the sounding radar. And also it has a lander. It's called the Philae lander. And the lander is what you see here. Also, we launched Rosetta in 2004. So Rosetta was designed in 1998. It was launched in 2004, and it rendezvous with the comet in 2014, which is mean that from development to meeting the comet, it's 16 years. So 16 years between when you start to when you reach the body, and 25 years end-to-end project lifetime, which is mean that when we arrived on the comet, you're talking about a technology that is roughly 20 years old. So that's an artist rendering, and that's the lander here, and that's the sounding radar instrument that I will be talking about, which is called the Consort. So we expected that the landing on the comet would be an easy exercise, because previously to this mission, the comet was known to be very smooth bodies, very easy to land, and the mission was designed for a comet named Vertinan 2, and Vertinan 2 was a small comet. It was about 500 meters in diameter. But unfortunately, during the lifetime of the mission, we missed the target of Vertinan 2, and we have to switch the spacecraft to another comet, which is 67P. And 67P was a bigger one, and it was more challenging. So basically, in a very easy word, what does that sounding radar instrument, what we want to do, that we want to understand the ice distribution inside of the comet. How much ice is there? How much the dust is there? What the type of dust we have? And use these informations for future monitoring of the comet and how it evolved in each time it go around the sun in the solar system. So when we started to approach the comet, we started to go to these very crazy orbits, because it's a microgravity environment. So it's not like orbiting the moon or Mars, where you have a gravitational body and you can go with high-speed orbit. This is very delicate orbit, and you have to approach it in a very specific way. At our big surprise, when we started to approach, the comet started to take shape, and we start to see it for the first time, and then the comet revealed itself as this. So to our big surprise, the comet was not smooth as we expected, and it was big. And now we have 2 months to decide where we're going to land with a 20 years old technology on this. This is rough, this is microgravity, it's a dusty and it's icy, and the surface is hard or fluffy. At that time we have no idea, and we have to design the landing experiment to do that. So just to give you an idea, this is the size of the comet as compared to the city of Los Angeles. And I know many look to this image and they think that the comet has hit the city of Los Angeles, but unfortunately it haven't done yet, because the traffic is still as bad and everything, it's just so horrible compared to here. So the comet is very dark, and actually if it is at night in the sky, if this comet is crossing in the sky in full size, if it is only 100 kilometers away, you wouldn't even be able to see it. It's so dark because it's rich of carbon material. So we started to prepare our landing, and this is the image of the comet. This is the real image of the spacecraft. This is from the navigation camera. And then we started to send the lander. So the lander, this is the real image of the lander separating from the spacecraft. So I know that many of you have watched the movie of landing on Mars and the 7 minutes of terror, from when you enter the atmosphere to the reach your surface, and you have this deployment of the airbag. It's 7 minutes of terror. This is 8 hours of terror. And the landing took 8 hours, and we are landing on a body that we have no idea where we're going to land. And also we are landing with a lander that is 20 years old. And it's not made by one space agency, by multiple space agencies, because it's a European Space Agency mission with a NASA contribution. So as we land, we started to see the surface, and we were about to land here. And again, we see the comet is very rough. And then we started to approach more, and while we're landing, we started to see some of the features. So this is where the position we land. Exactly. Yes, while we're landing, we start to see some of these features here that are in the size of the Eiffel Tower, that are made of ice, and we don't know what these are. So we start really see the wonderland of cometary material. And this is exactly the spot where we landed. And this is the real image of the footprint of the lander. Now the lander is basically in the size of this podium here. This lander does not have any propulsion. It is landing by gravitational attraction, and it has feet to anchor. After we landed, it was on all the news, people hugging each other and kissing each other, very happy that we land. But when we started to operate the radar, we started to see this. So this is the power we receive. This is the time in second. So we see that the power goes ups and down, ups and down, ups and down, ups and down. If the lander is static on the surface, the power should not change. I mean, the signal power we get from it should not change. If it is moving, if the power is changing, this is mean that the lander has not landed. And so then this information started to communicate between the mission operation, and then it was true, the lander was moving. It is pumping on the surface. So imagine you have a lander that lands on a place you don't know and is bumping, and you don't know where it is bumping, and you don't know where it's going to stop bumping. And the comet is a microgravity, so if you bump sufficiently with high speed, you can leave the comet. And the worst nightmare would be that you hit back the spacecraft. I mean, we don't know. I mean, with the scenario we have been, it was very bad. And so you can see the feeds here. Actually, I'm not sure. Oh, so you can see that here are the footprints of the pumping. Here, the 3 footprints. And then here, more footprints. Here, and then it was like crazy. I mean, we're searching where the lander is. And that's the search for the lander. I mean, the lander was moving for a couple of hours and then stopped. But we don't know it has stopped. We have no idea where is the lander. And now that this lander is operating for about 70 hours, collecting the data and telling information about the physical properties of the comet. But the big question, where are these physical properties? They are in this area or in that area, in the dust or in the rock. So we started to look to the roughness of the comet, and we find it's very rough. It's rich in boulders. So the lander could be in the shadows of one of these boulders. And then we started really to see for the first time that there are smooth unconsolidated areas and rough consolidated areas on the surface of the comet. And all this information, we thought we would never see the comet at this resolution at all. And finally, we see these goosebump, which are the big sinkholes, or not, it's a big holes in the surface that show you the inner side of the comet and what it is made, and these collapse on the exposed area of the comet that show that the subsurface is rich on ice. So now, remember, we talk about radar. So how the radar has come helpful. This is how the radar in locating the spacecraft. The experiment is designed in such a way that the lander will transmit a wave, and that wave will go across the video, and that wave will go across the comet body and will be measured by the spacecraft. So if we know the distance between the spacecraft and the lander, which theoretically we should know, but we don't, and we measure the time of the traveling wave, we can know the dielectric property, or basically the inner property of the comet. So we reversed that. We assumed the wave velocity inside the comet, and we know the spacecraft where it is, and now we have to find where the lander is. And we published it in Science where would be the location of the lander. And that was published, and for a year and a half, the camera of the main spacecraft was looking to other areas because people who are working on the camera have other suggestions where they can find the lander. And when we started the final descent of the Rosetta mission, the spacecraft, the Rosetta mother spacecraft, started to go in a spiral orbit to approach 67P, the comet, and then to collapse on its surface. And just few days before it collapsed on the surface, it was able to locate the lander in a ditch here, underneath that rock, you see? And that's the lander. So this is the first time we lose a lander and we are able to operate it while it is lost. And we are able to find it after it is dead. And a divine hand have come to save that mission. I mean, but the amazing thing is that how you work on the development of such experiments for decades of your lifetime. And then when you land, you face all these challenges. You lose the spacecraft stops responding because of the solar panel they are in the shadows, and then the shadows change and then start operating for a few hours, sending you a signal, and you start to look at it where it is, and then it's dead again, and then you have to go with a big spacecraft to collapse on the surface to find it. All of that to show us that space missions are very complicated, but yet in this complexity is where we find the most important result. And in this complexity, we understand nature. Nature is not simple at all, at all. And nothing in our life, the thoughts, even our views of how we as people, we think and how we interact, nothing is simple because we are part of nature, and everything that is reflected in nature is reflected on us. So nature is not simple, we are not simple. So when you hear people talking simplistic stuff about people or nations or anything, you know that something is wrong, because nature is never simple. So the big honor I really have is I was a graduate student when the Rosetta mission started on, and I was a member of the team in JPL who helped in the landing, who helped to operate the radar, and who helped to locate the spacecraft. And just a few months ago, the Berlin Museum of Natural Science, they put a few figures of the astronomer who changed the history of astronomy, and amazingly, the people who contribute to the land